Good evening. I'm Frances Hellman. I'm chair of the physics department, and I'm delighted to be the host for this year's Regent's lecture, which is going to be presented by Steve Koonin, who is chief scientist of BP. In a lecture of this with this distinguished a crowd, I actually don't even have I don't get to introduce Steve. I get to introduce the person who is going to introduce Steve. So, at any rate. Before I even get that far, let me point out that there's a couple of house rules for this lecture. Please allow our speakers and your fellow audience members to enjoy tonight's program without interruptions. So there'll be plenty of time at the end for questions, but we'd appreciate it if everybody could sort of hold their questions till the end of the talk. Please turn off your cellular phones and no flash photography. No banners or signs can be displayed. They will be removed if any show up. Please do not shout or engage in any action that disrupts the event or that prevents the speakers, either of them, from being heard or being able to continue. And we ask that everyone remains in their seats during the presentation. So basically, we want this to be a nice, friendly presentation, and hold your questions till the end. So without further ado, I would like to start by introducing the introducer. So it is my great pleasure tonight to introduce a name and face that is going to be, I think, very familiar to all of you, Dr. Steve Chu, who is an esteemed professor of physics, as well as a professor of molecular and cell biology, and the director of the Lawrence Berkeley Laboratory. His career, which is extremely distinguished, began actually as a graduate student here in physics at Berkeley, working with Eugene Cummins and on some other faculty, actually using lasers and some tabletop techniques to measure parity violations, some very, very early and pioneering experiments in that area. After leaving Berkeley, he went to AT&T Bell Laboratories, stayed there till 1987, went to the physics department and applied physics at Stanford University, stayed there for 17 years before returning to what we think of as his true home, which is here in Berkeley. Steve, as I think probably all of you know, won the Nobel Prize in Physics in 1997, an honor he shared with Claude Cohen-Tanuji and Bill Phillips for the development of methods to cool and trap atoms with laser light. These atom trapping methods are still central to the study of fundamental phenomena and in measuring a lot of very important physical quantities with unprecedented precision. Since coming back to Cal, Steve has remained active in his own research, which continues with a lot of these atom trapping techniques, as well as using lasers to manipulate and study biological systems. But he's also led LBL to becoming a world leader in the broad problem of energy, which many would argue is one of, if not the leading scientific challenges facing the world. This included co-chairing an international inter-academy study, Lighting the Way towards a sustainable energy future, transitioning to sustainable energy. And many of you know how important the energy research has become at LBL under Steve's presence. So it was Steve Chu's incredibly excellent idea to nominate Steve Koonin, where's Steve gone? Steve Koonin over here, to be the Regent's lecturer this year. And so it makes the most sense that I should now turn the podium and the microphone over to Steve for that part.
Thank you. I'm in big trouble because my introduction will be shorter than the introduction to the introducer. and so at least we'll give you time for a talk. Steve was born in Brooklyn, New York, and educated at Caltech, receiving a BS in physics in 1972. And he got a PhD in theoretical physics from MIT in 1975. A little louder, okay. And so he got his I'll say that again. He got his PhD from MIT in 1975, and from then he went directly to becoming a professor, joining the faculty at Caltech in the physics department in 1975. In 6 years, he advanced very rapidly, became a full professor at Caltech. By then, he was at least 22. And then in 1995, he served as a provost until 2004. And he has many interests: theoretical nuclear many-body physics, computational physics, nuclear astrophysics, and much more recently, global environmental science, more recently being at least in the last 5 or 10 years. He won in 1999 the Ernest O. Lawrence Award in Physics from the Department of Energy. He's a fellow of the American Physical Society and the American Academy of Arts and Sciences. And he's been serving on numerous advisory boards from the National Science Foundation, the U.S. Department of Defense, and the Department of Energy. He's currently the chief, I want you to hold the thought that he served on many advisory boards to the Department of Energy. Just for a moment. He's currently chief scientist of BP at London, formerly called British Petroleum, but now I guess it's beyond petroleum. BP is the second largest independent oil company in the world since 2004, and actually BP America is one of the largest corporations in the United States. As chief scientist, Steve Koonin was responsible for BP's long-range technology plans and activities, and I think he played a major role in within the company in designing this Energy Biosciences Institute. He also oversees many of the other major research programs around the world. And so now, what I wanted you to hold a thought was, despite the fact that he's very familiar with the Department of Energy, he was able to, hopefully with a straight face, go back to BP and say that the combination of the University of California, Berkeley as the prime contractor, if you will, with University of Illinois, Champaign-Urbana, and Lawrence Berkeley National Lab, out of all the institutions around the world, they chose UC Berkeley for this initiative in biofuels. It's an incredibly, very open initiative. The vast majority of the work will be openly published in the literature. The proposals and what they're funding is actually on a website. It's very, very open in terms of what's going on. And so I think they're taking a very long-term view. And I personally wish that other companies major companies around the world would also take this long-term view. It's not philanthropy, but it's something where they chose university partners in order to push knowledge forward that not only BP but other companies can use. So with that, I will stop. It was a great pleasure that he's here today, and he's a really smart guy, a fabulous scientist, and a great speaker. Steve,
Good. Thank you.
Podium's yours.
So it is a great pleasure to be back here. My connections with Berkeley, both the campus and the lab, go back more than 30 years, and it's a pleasure to see so many friends here again, both old friends and people that I've come to know in the last 5 years or so here at Berkeley since my time at BP. So I joined BP 4 years ago, almost to the day, with the brief to try to help them plot what came beyond petroleum. And like any good academic, I figured I'd better understand the energy landscape before I tried to do that. I had not been involved in energy matters before that. And so I set about, for about a year and a half, learning energy. I think I was probably the highest paid graduate student in the world for those many months. And as I came to understand things, develop my own mental picture, understand the facts and so on, I went out and about talking to lots of people. And a common reaction, both inside the company and maybe equally surprisingly outside the company, was, gee, I didn't know that. And given how important energy issues are and how prominent they are in society today, I didn't know how important they would be when I joined BP 4 years ago. The price of oil 4 years ago was like $25 a barrel. And I wrote a memo to the chief economist at BP at the time saying, what would happen if the price got to $40? And he said, don't worry, it won't happen. We still make money in this business, despite sometimes making errors like that. I figured it was important to be out educating people about the facts, pretty much. I'm trained as a physicist, and so what I want to tell you will largely be factual. It'll be quantitative, analytic, and so on. And I want to try to distinguish clearly between what we know, what's my own judgment or opinion, and what is outright speculation. And people don't always do that in talking about energy. Also, I should say that my time frame is about 30 years or so, and so you won't hear me say the word fusion except for what I just said. Good. Maybe if somebody asks a question, we'll say it. So what I want to do first is to try to paint for you the energy landscape which forms the necessary backdrop against which we can talk about energy technologies. Now, when you start talking about energy technologies, the first thing you realize, it's not just about the technologies. Energy is so pervasive in society that you really have to understand the societal context, the economics, the politics, the cultural context, and so on. Once you understand that, you can then start talking about the technologies. We came to understand that there were 4 drivers of the energy scene that are likely to be important over the next several decades. And what I want to do is take you through each one of those drivers in turn, a little bit of the factual context, and then we'll turn to the technologies and the policies that are important in trying to realize their development and deployment. So the first driver is demand growth, the anticipated strong growth in demand in the next 30 years. The second is challenges in providing the supply to meet that growing demand. The third is associated with the security of that supply. How confident can the consuming nations be that the energy is going to be there at a reasonable cost? And then the environmental impacts associated with energy. We'll start off with the growth in demand, and the headlines there are, first of all, strong growth in demand driven by GDP growth as well as the world's population growth. Some modulation of the kind of energy people want by the growing urbanization of the world, and then some discussion about demand management or conservation and efficiency. So I like to start off with this chart, which for me is so iconic about what's going to happen with the world's energy and what has happened in the past. What's plotted is for 24 years of data, the average, well, not the average, the primary energy that each person uses per year in gigajoules. For those of you who are technical, I apologize for the proliferation of units. You'll see gigajoules, barrels of oil equivalent, tons of coal, and so on. Of course, you can convert from one to the other with a little bit of time, but what's important are the relative magnitudes of all of these things. Plotted against the economic activity per person, GDP per capita in constant dollars. And what you see are trajectories for different countries over this 24-year period. Lots of things are interesting when you study the data. Most obviously, perhaps, is how out of whack the US is with everybody else. Almost, but not quite, the highest per capita energy use of any country on the planet, but surprisingly to many people, growing pretty slowly, at least over the last 20 years, not going up much at all, nearly horizontal line. There are another group of countries in the developed world, the EU and Japan, that have per capita energy uses about half that of the US, but GDPs that are only about 2/3 that of the US and are also growing fairly slowly, although Japan is interesting the way it shoots up like that. There are some other countries that are interesting on this chart. Look at the way Ireland takes off like that. It's quite amazing. If you've been to Ireland recently. Russia is an interesting case, non-monotonic, perhaps, right? And all the turmoil in the 1990s that took place in that country made it go down like this and then go back up like that. And then there is a broad swath of countries in the developing world, China, India, Brazil, and so on, whose energy use more or less increases on a universal trajectory as their economies develop. It is really interesting that this is more or less universal. I find that quite interesting. Nobody's given me an explanation for that. A couple of years ago, about 3 years ago, I was in China. And at that time, the Chinese government had announced that they were going to quadruple their GDP and only double their energy use. And that would have put them out here somewhere. And I said, that's wonderful. How are you going to do that? We'd love to help you in BP. Meanwhile, what's happened is China, of course, has more or less fallen into line with everybody else. What's sobering about this picture is two. One is that there are about 1 billion people between the US and the rest of the developed world. There are about 2.5 billion people down here, and then there are another 2.5 billion people that aren't even on this chart. And since nobody's energy use goes down as they get richer, what we can expect is that there will be strong growth in energy demand simply due to economic activity. If you then combine that, well, here's a nice chart that illustrates that, perhaps. This is the absolute energy demand now for 30 years in the recent past, shown for 7 different regions of the world. And yes, North America is going up, Latin America, Europe, Russia, as we've seen, does that. But what catches one's eye is Asia, like so. And again, with per capita energy uses that are just a fraction of what they are in Europe or the US. This strong growth due to economic development, together with the population of the world rising from currently 6.5 billion people to about 9 billion people by the middle of the century, is going to drive strong growth in demand for energy. There's no question about that. This is what it looks like out to 2030 from more or less the present, and what is expected is about a 50 to 60% growth in energy over the next 25 years. 3/4 of that growth will come from the developing world and 1/4 from the rest of the world. And what's interesting, as shown in this chart, is the energy use broken down by sector. For most people, when you say energy, they immediately think automobiles and oil. But in fact, as you can see from this chart, transport accounts for only about 22% of the world's energy use right now. Much larger fractions go to power, about 40%, and to heat in buildings and industrial processes, also about 40%. So in your mind, just imagine transport 20%, 40% electricity, and 40% heat and power. Of course, those numbers vary quite a bit in different locales. In California, transport accounts for 40% of the energy that is used in California. In the UK, it's about 32% transport energy, and so on. So the numbers change around the world, but worldwide, these are the numbers. As the world gets richer, transport will grow somewhat disproportionately, since mobility is something that developing countries like to purchase. Power will also grow somewhat disproportionately, since the clean form of electricity is an energy that many countries like as they get richer. Okay, let's talk about the challenges associated with supplying that energy demand. And the answer here is that, first of all, there are significant resources in the ground. The world is not running out of energy anytime soon, although for various reasons we expect to see a rise in so-called unconventional sources of energy. This chart is another of these really simple but interesting charts. It shows where the U.S. got its energy over the last 150 or 160 years. And if you look back just before the Civil War, the U.S. got 90% of its energy from wood and only 10% from coal. As the Industrial Revolution set in the late 19th and early 20th centuries, you can see that coal comprises the great bulk of energy. As the transport revolution set in the middle to late 20th century, oil becomes a bigger fraction of the energy that the country used. Gas, a wedge that came in starting in about 1940 or so, a little bit of nuclear in the last 3 decades, and renewables, about which we will have much more to say in a while, tiny bit up at the top over there. That's non-hydro renewables, by the way. So lessons from this chart are, first of all, that energy technologies do change. They change in response to technology, demand, economics, and to some extent the political situation. But they change very slowly. You'll notice that the timescales here are decadal timescales. And as we talk about the CO2 problem and perhaps security of supply problems, it's sobering to realize that we've got about 30 years to deal with those problems, and that's just 3 bars on this graph. The other amusing thing is that the absolute amount of energy that the country got from wood in 1850 is equal to the absolute amount of energy it got from wood today. It's just that all the other demands have gone up so dramatically. Where does the world get its oil right now? Get its energy. Mostly it's oil, as you can see. The biggest fraction is oil, but it's been coming down as oil comes out of power and heat and is localized in transport. Coal has been coming down as a fraction. It's still about 28% of the world's energy, but in recent years it has come up, and we'll talk about why that is in a moment. Gas has been climbing but has leveled off, and nuclear and hydro, not much change at about 6% of the world's primary energy over the last several decades. If you look at the history and projections of where the world will get its energy, assuming plausible historical growth rates, right now the world gets roughly 80% of its energy from fossil fuels, coal, oil, and gas in the proportions shown. Another 10% actually, maybe a bit more, comes from biomass and waste. That's a surprisingly large number. That is not biofuels. That is people burning wood and dung in the developing world for heat and light in their houses. If we go out to 2030, assuming these growth rates, even with the strong growth rate in other renewables, which are geothermal, solar, wind, tide, and wave, you can see that by far the largest proportion of the world's energy will still come from fossil fuels. This is, of course, business as usual. The world does not have to follow business as usual, but in fact, there are strong tendencies to do so, as we'll see in a bit. Well, the obvious question is, if fossil fuels are likely to be the most important part of the picture for the next 25 years, are there sufficient fossil fuels in the ground? I believe the answer is yes to that question. This shows for the three fossil fuels, oil, gas, and coal, how much is known to be in the ground. How much is there yet to find, and how much might there be in more unconventional sources? And you can see for oil, this is all on a common energy scale, there are 41 years of proven reserves at current production rates. R to P is reserves to production. How much is known to be in the ground versus how much we extract every year. The geologists, who are pretty good at estimating such things, believe there's an equal amount yet to find. And then there are vast amounts of unconventional oils, tar sand, shale oils, and heavy oil, and so on. The Orinoco Belt in Venezuela contains very heavy oil, estimated at 1.5 trillion barrels or so of heavy oil. We'll talk about how much that is in a moment. For gas, the situation is comparable, about 70 years at current production rates, about the same yet to find, and great amounts of unconventional gas, so-called tight gas, or if we could ever learn how to extract them safely, methane hydrates in the permafrost in the bottom of the ocean. Coal, however, is the big factor in all of this. The world has at least 160 years of coal at current consumption rates. No one has really gone exploring for coal, and some people estimate as much as 1,000 years of coal. So I look at this, and it looks to me like there is plenty of carbon in the ground. Let me focus in on oil. You will have heard many people talk about the peaking of oil production, Hubbard's peak. This is data from the IEA a few years ago. It shows how much oil is available at what price. How much does it cost to get it out of the ground? And for the last 150 years or so, the world has produced 1 trillion barrels of oil at prices that are less than $20 a barrel. OPEC countries in the Middle East are estimated to have about another 1 trillion barrels, and other countries outside of the Middle East, conventional oil, about another 1 trillion barrels. And then there is a succession of more exotic forms of oil in the deep water. You may know that companies like BP, Exxon, Shell, routinely operate in about 6,000 feet of water and drill down another 20,000 feet and extract oil, and it is economic, even at $30 a barrel. Enhanced oil recovery is a big one. The world only gets out 35% of the oil that it knows to be in the ground on average. Every little bit that one can do in terms of chemistry, physical manipulation, and so on to get more oil out is very important. And then there's other oils, heavy oil, oil shales, and so on, all of which can be produced at prices that are economic relative to today's $100 a barrel. How much will the world need? In the next 25 years, the world will need 1 trillion barrels, which is the width of this red bar. And you can see that it looks like, according to these estimates, 4.5 trillion barrels are available in the ground. A lot of people say that the countries in the Middle East are not fully forthcoming about their reserves. Even if they're wrong in this chart by a factor of 2, it still looks to me like there's plenty of oil. As one of my senior colleagues in BP has taught me, what happens with oil production is not so much about the situation below ground, but the situation above ground. Politics, economics, technology, and so on. Couple words about security of supply. There is a dislocation of resources, at least for oil and gas. The oil and gas are in the ground, not where the main consuming countries are. And so there is a dislocation and a trade there, and a reliance upon the stability and security of distant oil sources, and to some extent gas sources, in the consuming countries, and a growing dependence upon imports. This is the one chart I want to show about that situation. It shows for the 3 largest energy markets, North America, Europe, and Asia Pacific. For oil, those 3 markets consume 78% of the oil produced every day. But they have only 10% of the conventional oil reserves. For gas, the situation is not much happier. 61% of the consumption with only 15% of the reserves. While for coal, you can see that the consumption is much more evenly matched with the reserves. To put it simply, the oil is where the people aren't, and the coal is where the people are. And so you might imagine, as countries become concerned about security of supply issues, they will turn increasingly to coal. And that, in fact, is happening to a large extent in China already, and greater extent in the US as well, and that is responsible for that uptick in coal that we saw in one of the charts I showed you previously. Okay. Last of the 4 drivers, environmental impacts. These are of 2 flavors. One is local pollution. I lived in Los Angeles for 30-some-odd years, and during my time there, despite a great increase in the population of the basin and in the economic activity in the Los Angeles area, the air got palpably better. That was a result of increasingly stringent regulations that were backed up by technology developments. So the technology is there. It's there at cost. If you go to Beijing or Mumbai these days, you'll see that the local air pollution is a serious problem. And eventually, those countries, I think, will pay the additional cost to clean up the local air pollution using existing or technologies that derive from existing methods already. Climate change, however, is another environmental impact that is in many ways much more problematic, and so I want to spend some time talking about that. CO2 concentration is going up, and it's going up due to fossil fuel use. We know that unambiguously. This is a graph up to 2004 of the CO2 concentration as measured in Hawaii in parts per million. In 1958, it was 320. Before the Industrial Revolution started, it was 280. And you can see that it has climbed more or less steadily apart from the annual variations shown here. It's currently at about 385 and goes up by about 2 ppm every year now. The global temperature is also increasing. This is the official NOAA surface temperature record, and you can see that particularly since about 1975 or so, there has been a steady monotonic increase of the global temperatures. Although interestingly, there has been a leveling out over the last 8 years or so. Remains to be seen exactly what's going to happen. We have other indicators of climate change: thinning of the Arctic ice pack, the advance of spring every year, thinning of glaciers, etc. There is a plausible causal connection between these 2 things. Arrhenius worked it out semi-quantitatively more than 100 years ago. If CO2 goes up because it's a greenhouse gas, the temperature should go up. But we are looking at a 1% effect in a complex and noisy system. The additional heat radiating from the sky to the ground due to the increased CO2, if we were to double CO2, is about 3 watts per square meter. That's on top of a natural flux of about 350 watts per square meter, so a 1% effect. The scientific case is also complicated by natural variability and to some extent ill-understood forcings, particularly aerosols that are produced by human activities. Moreover, the impacts of higher CO2 are rather uncertain. You can make some broad statements that the hydrological cycle will run faster, that there will be some drying in the subtropics, that the poles will warm faster than the rest of the globe. But beyond that, it becomes difficult to be precise. Nevertheless, many people talk about twice the pre-industrial concentration, so 550 parts per million, as a stabilization target above which will start to exert dangerous influence on the climate system. If you just take these data and extrapolate them naively, that 550 ppm is reached by about the middle of the century under business as usual. So independent of the scientific questions here, I think it's pretty fair to say that precautionary action is well warranted, and the real questions to try to answer are what could the world do about this, and what will the world do about this? And those are the things I'd like to turn to now in discussing climate change. Before I do that, there are two crucial things you have to understand about CO2 in the atmosphere in order to think about solving the problem. And that's illustrated by this graph, which shows fossil fuel emissions in gigatons of carbon now per year, historically up to 2004, and then extrapolated at a 1.5% compound growth rate going forward. When this chart was made in 2005, 1.5% rise for the emissions seemed like a good number. In recent years, it's actually been about 3% rise, so it's going up even faster than this, again, largely driven by economic activity and the resurgence of coal. This is how much we are putting up into the atmosphere every year from fossil fuel use. Not all of it stays, about half of it stays, but that contribution to the atmosphere every year drives a similar increase in the concentration. And this is, of course, what's important for the climate. Now, what's interesting is that the lifetime of CO2 in the atmosphere is very long. It's about 1,000 years, much longer than the rise time of this curve, which is 60 years or so. And so we put the carbon up there, it effectively stays up there. It means that the CO2 is accumulating in the atmosphere. And that means if we manage to make a modest reduction in emissions, according to the green line, like that, let's say bend emissions over by 10% or so, it means that the concentration will continue to rise, but rise a little bit more slowly. And if you believe that the danger line is, let's say, 600 parts per million, all you have done is delayed the time at which you cross the dangerous threshold, but haven't prevented it. And a good rule of thumb is that every 10% reduction, it buys you about 7 years. And so if we really want to rein concentrations in, we need to make drastic reductions in the emissions. For example, if you want to stabilize the concentration at 550 parts per million, according to one of these green trajectories, you need to follow an emissions trajectory that is either dramatically decreased right now, or we let the emissions go up a bit and then cut back harder later. And similarly, if you want to stabilize at 500 or even 450, you follow those red or blue trajectories. So you see that we need to cut emissions by about a factor of 2 from their current value, and that's in the face of a doubling of energy demand by the middle of the century. And so we need to cut the carbon intensity of our energy system by about a factor of 4. And for reasons that I'll explain in a minute, we need to do it pretty quickly. Beyond that technical discussion of the barriers to stabilizing CO2, there are social barriers that make it difficult to have meaningful emissions reductions. The first is that the climate threat is intangible and diffuse, and as we've seen, can be obscured by natural variability. 3 years ago, we had a pretty disastrous hurricane season in the Gulf of Mexico. Katrina was probably the most memorable of those hurricanes. And you were reading in the newspapers, symptom of global warming, et cetera, et cetera. The year afterward was a particularly quiet hurricane season, and the year that just finished was about an average hurricane season. There's a lot of variability here, making it difficult to attribute things to the climate change phenomena. I would contrast that with ozone or air pollution, which got real for everybody when NASA produced this picture of the ozone hole over the South Pole. So it's a little bit hard to make the climate change discussion real for people. Second, energy, as I've shown you, is at the heart of economic activity. Again, it's not like CFCs, where there were plausible substitutes, although at some difficulty and expense. Maybe at the heart of the problem is that the CO2 timescales are poorly matched to the political process. Energy infrastructure. Power plants last 50 years, houses last 100 years, automobiles last at least 20 years or so. The buildup of CO2 takes decades, and it lives for 1,000 years, as I mentioned. So it's hard to make changes rapidly, particularly when our political cycle is 6 years and the news cycle is about a day. So it's hard to keep people's attention focused on this. There will be the inevitable distractions. A few years of cooling, economic downturns, as we're about to see in this country, unforeseen expenses, wars, tsunamis, et cetera, right? Because this is going to cost money to reduce emissions. And also important is that the amount of emissions, the economics associated with them, and the priority of the climate change threat that people give vary greatly around the world. This chart shows CO2 emissions per capita against GDP. Again, it's very similar to the energy chart that I showed you opening up the talk. Developed world pretty high per capita but growing slowly. Developing world low per capita but developing rapidly. There are a couple of interesting anomalies on this chart. France, you may remember, was in line with everyone else on the energy chart. It's low here because France gets 80% of its electricity from fission. Similarly, Brazil is low here compared to the other countries because A, Brazil has a lot of hydroelectric power, and B, Brazil powers about half of its road transport with carbon-neutral bioethanol. Now, those are indications of how we might be able to reduce emissions. It turns out, when you look at the numbers, that in this century, emissions from the developing world will be more important than those from the industrial world, the OECD countries. The developing world emissions are growing at 2.8% a year, whereas the industrial world emissions are growing at only 1.2% a year. If you draw a picture, emissions versus time, the developing world goes up rapidly, the industrial world less rapidly. They cross just about now, actually. You may have read in the papers that China as a whole is just about equal to the US in terms of absolute emissions. You put those numbers together, and there are a couple of interesting things you can conclude. When these two contributions are equal, i.e. now, every 10% reduction that the industrial world can make in its emissions is compensated by less than 4 years of growth in the developing world. 4 times 2.8 is bigger than 10%. And of course, we've not yet managed in the industrial world to make a reduction of 10%. And second, if you took India's per capita emissions and made them equal to Japan's, which are among the most emissions light of the developed countries, global emissions would go up by 40%. And remember, we got to go down by a factor of 2. So, as we say in the business world, this is a challenge. All right? Technology is going to be really important to get this right. And so I want to turn to the technologies now. One last chart about emissions before I talk about technologies. This shows, about a decade ago, where did greenhouse gas emissions come from? What different activities? And what you can see is that 2/3 of the emissions come from energy-related activities, most from power, 24%, a smaller fraction from transport, and industry and buildings making up the heat emissions that I talked about previously. But interestingly, land use is big. Land use is deforestation, people cutting down trees and burning them, putting that carbon up into the atmosphere. Agriculture, 14%. Fertilizer, oxides of nitrogen, and so on, as big as transport, and waste a little bit more. We're paying a lot of attention to this, and rightly so, but there are equally large contributions, largely unregulated, to greenhouse gas emissions that we should be working on as well. Okay, let me turn to the technologies and the policies. And I think the first thing to learn about energy technology is that it's different. It's not like IT, in which we have a lot of experience in innovation. It's not like the life sciences, where we also have a lot of experience in drug development, for example. There are 4 aspects of energy technologies that really make it different. The first is the scale. Energy requires large infrastructure. A power plant can cost $1 billion or more. A single BP project offshore is a couple of $1 billion. Pipelines, et cetera, cost a lot of money. It involves large amounts of material. The world uses 5 billion tons of coal a year, 5 gigatons, 2 billion tons of oil. So there's a lot of stuff involved. And there are large numbers of units. Right? I don't know how many 100 million automobiles there are in the world right now, but I do know, interesting factoid, more automobiles will be built in the next 20 years than were built in all of the 20th century. Lots of units. This scale requires large amounts of capital, and it requires that we try to leverage existing infrastructure as much as possible. I think that necessarily means that large companies need to be involved in the innovation chain early on, and that is one of the rationales for the EBI, which I will come back to a little while later. The second is ubiquity of energy. Energy is so common in everyday life for heat, mobility, transport, and light that we hardly think about it. And that means that there are many people interested in energy. Consumers, producers, governments, NGOs, and so on. And their interests don't always align perfectly. And as a consequence, energy change is slowed down. The third I've mentioned already is the issue of longevity. The large infrastructure lasts a long time. But there are also interoperability issues. For example, BP cannot unilaterally change the kind of gasoline that it makes because it has to work well with all the cars that are out there already. And so that slows things down. And then finally, there is the issue of incumbency. We already have pretty good technologies for providing heat, light, and mobility. If we're going to introduce a new technology, it has to compete on cost, even though it may not provide any qualitatively new service to the end user. So, for example, when cell phones were first introduced broadly, they gave you a new capability. You could talk on the run, and people were willing to pay a lot of money for that. If I provide a new way of generating electricity, at least to the consumer, it looks just like the old way of doing it, right? And so there is this issue of incumbency, never mind the vested interests associated with producing and transmitting the energy already. For all these reasons, energy is different. Now, you can make a long list of energy technologies. Here they are. How do you navigate your way through all of this? A common statement is that there are no silver bullets. Right? We should be pursuing everything. To my way of thinking, that's exactly wrong. We've got about 30 or 40 years to deal with these problems, whether it's security of supply or climate. We've got to find those technologies that have the capability of having the biggest impact at the lowest cost. Or the way I like to say it is, some bullets have a bigger caliber than others. Another ballistics analogy is that we need silver buckshot or something like that, right? Okay. So how do we assess energy technologies? The first to my mind is current technology status and technical headroom. Windmills have been around for a couple of millennia. There will be incremental improvements in wind technology, no doubt. But if you compare that to the kind of improvements that you might imagine due to our developing knowledge of biology and biotechnology, the bio looks really interesting from a technical development point of view. Again, another reason for the EBI. There are budgets. People forget about this. There's the economic budget, as I mentioned already. You've got to compete on cost. There's energy. There's emissions. There's materiality. People often forget about how things have to scale. You have to produce a terawatt of power if you want to have a 5% impact on the world's energy demand at the middle of the century. For a big company like BP, scale is very important. There are other costs, reliability, intermittency. The wind doesn't blow all the time, the sun doesn't shine all the time in one place on the globe, and so there are issues associated with those renewables. And then finally, social and political acceptability. Nuclear, perhaps most obviously, wind, siting of wind farms, increasing discussion in the last few weeks about biofuels. I'm happy to talk about all of those in detail during questions later on. You also have to understand what problem you're trying to solve. And there are at least two distinct problems that technologies play into differently. We like to think about them as two axes. One is basically oil price, or concern about the availability of oil and gas, low oil price, high oil price, if you like. The other is climate change, low concern about climate change, high concern, if you like, low carbon price and high carbon price. And if you look at technologies in this two-dimensional space and consider first transport technologies, transport is all about liquid hydrocarbons. If you were not too concerned about climate change, you would be turning coal into liquids, gas into liquids, producing heavy oil, and so on. If you look at demand-side options, ways of improving the efficiency or hopefully conserving the oil that we use, you look at hybridization, wonderful idea, vehicle efficiency, lightweighting vehicles, and so on. But on the supply side, if you look in the upper right where you would really like to be, addressing both security of supply and climate change threats, there's only one material circle in our judgment, and that's advanced biofuels, not conventional biofuels, which is over here. Little tiny circle up on the right, carbon-free hydrogen for transport, provocatively shown like that, and I'm happy to talk a little more about that later on. Okay? So let me talk just briefly about liquid hydrocarbons. They are wonderful for transport. If we didn't have them, we'd probably have to invent them. Okay? This shows the energy density, gravimetric energy density, and volume energy density of various ways of powering a vehicle. Gasoline and diesel are way up there at that red dot. The best DOE goal for hydrogen is over here. Batteries are way down over here, about a factor of 50 times less than gasoline. More energy per unit mass than TNT. It's pretty good. So for mobility, where you need to carry a lot of energy with small weight and small space, liquid hydrocarbons are likely to stay around for quite a while. For liquid hydrocarbons, the real issue is where do you get your carbon from? I'm a physicist, and I trust the chemists and chemical engineers to invent ways to decorate the carbon with hydrogen and oxygen. Right? And we have ways of doing that. Some people in the audience are experts at doing that, I know. We can turn them into fuels, we can turn them into chemicals, we can turn them into electrical power if need be. But the real question is, where do you get your carbon from? And so what I did a couple summers ago was to go through the exercise of asking, where did the US get its carbon in 1 year recently? And let's start with the transport fuels over here. In gasoline, in a year, the US uses about 450 million tons of carbon a year. In diesel, about 200 million tons of carbon a year. So you add it all together, 650 million tons of carbon a year are used in transport and emitted out to the atmosphere. Let's suppose we wanted to make an impact on that transport at the 15% level. So I want to try to get 15% of the carbon from somewhere else because we don't like crude oil, either because of security of supply or because it's a fossil fuel and adds to CO2 emissions. 15% is the height of this red bar. And now we can look at other sources of carbon and ask, how do they compare with the height of that red bar? Coal, plenty of carbon. The US, as I mentioned, uses about 1 billion tons of carbon a year in the form of coal. It could easily use more. Natural gas, similarly, there's quite a bit there. Other petroleum, natural gas liquids, propane, and so on. The problem with all of these is that they're fossil fuels. They will add to CO2 and or deteriorate our security of supply situation. So we don't like those. A lot of people are interested in using agricultural products to get their carbon from. The entire US corn crop in one recent year was 120 million tons of carbon. So even if you converted it all to fuel with 100% efficiency, so no food for animals, no popcorn, no exports, right? you would only still make a 15% dent. Other crops are sort of interesting to look at through this lens: paper, soy, wood pulp, and so on. I love the edible fats and oils. Where is that? Somewhere there, right? You will read in newspapers about people powering their old diesel cars by kitchen waste, right? Willie Nelson, remember doing that? Great idea, right? The problem is there just isn't enough. You can't fry enough French fries to make a difference. You just can't. Scale is really important. Biomass today, the U.S. uses about 1 million tons of carbon a year in biomass, mostly in wood chips, in paper plants to make electricity. It's burned. U.S. DOE and Department of Agriculture estimate that about 650 million tons of carbon could be produced sustainably in the U.S. And so you can see from this chart, if you want carbon instead of petroleum, you're either going to dig it out of the ground as coal or you're going to grow it as biomass. And to my mind, this is one of the strongest, simplest arguments for pursuing advanced biofuels. For power, electrical power, if you're not interested in climate change, coal, plenty of it, easy to use, cheap. As you get interested in trying to be both emissions-free and respecting security of supply, there are a number of options that emerge. Nuclear, hydrogen power, wind being the most prominent of them. It is interesting and sobering to ask, where does the world get its electricity from? And this is in a recent year, 2004, 40% coal-fired, 20% gas, nuclear 15, 16%, and hydro 15, 16%, oil 7% and decreasing. The other 2%, most of that is biomass. When this chart was drawn, wind was 0.5%. It's now about 1%, so that's pretty good, not bad. Solar, 0.02%, 2 times 10 to the minus 4. I think it's now about 3 times 10 to the minus 4, right? Maybe 4 times 10 to the minus 4. Hardly matters. Small. Okay? Can we grow it? Maybe. But let's look at costs. Right. This shows how much does it cost to generate a megawatt hour of electricity by different methods according to the CO2 cost. How much penalty do you have to pay, either through a tax or a cap-and-trade system, to emit a ton of carbon dioxide? And what you see is that at zero carbon price, which is where the world is currently, most of the world, coal is by far the cheapest option, but it rises most rapidly because it has the most emissions per unit of energy delivered. Gas, natural gas, somewhat higher than coal, but rising less rapidly because it has more energy per carbon atom than coal does. Nuclear, flat. It doesn't emit, at least emits very little, and is pretty cost competitive with gas. Onshore wind, also flat, somewhat higher. Carbon capture and storage, of which there is much discussion. Methods for burning coal, capturing the CO2 and putting it under the ground where we expect it to stay, when the technology is fully mature, will be roughly competitive with onshore wind. What's interesting is that a lot of these curves cross somewhere between $20 and $40 a ton of CO2. And so I think you can say quite generally, and this is backed up by more sophisticated analyses, that unless your carbon price is at least $20 a ton, you're not serious. And if it's more than $40 a ton, it's too high. You're pushing the system too hard. Because $40 a ton is enough to induce a shift away from coal. Interesting numbers on this chart. Where does solar energy sit? Solar PV, photovoltaics, is constant as a function of carbon cost, but sits up at 250. Okay. So that might cause you to question whether the Million Solar Roof Initiative in California, which is going to spend, what, $8 billion in total, whether that is a wise investment if your goal is to reduce CO2 emissions. Another interesting number on this chart is transport. If you take a gallon of gasoline and say the carbon price is $40 a ton of CO2, how much does that increase the price of gasoline by? And the answer is 35 cents a gallon in the US or 5p a liter in the UK. That's pretty small on the scale of fluctuations that we've seen in the last several years. What that's telling you is that if you want to reduce CO2 emissions, power is by far the most cost-effective place to go, heat also. And those are cheaper by about a factor of 4 or 5 relative to taking it out of transport. And those numbers are true even if I am from an oil company. All right? That's what the numbers are. That's fortunate, by the way, because as you've seen, much more emissions from heat and power than there is from transport. All right, a couple words about efficiency, demand side reduction. Buildings use 40 to 50% of the world's energy. The technology exists today to reduce that demand by half. Okay? 50% cut. The problem is deploying that technology, consumer behavior, business models, and policy. To give you one example of the disconnect, I live in a leased townhouse in London. I pay the utility bills, and so I get big heat bills during the wintertime, but I don't own the infrastructure. The landlord owns the infrastructure, and so neither of us has an incentive to put in better windows or a better heater, and so on. Cities. Right now, 50% of the world's people live in big cities of 1 million people or more. By 2030, that fraction will go up to 70, 75%. Are there opportunities to optimize how we design cities? Transport of goods and people, building design, the flow of data, and so on. We BP are pursuing research programs to that end. Let me say a word about efficiency and conservation because they are not the same thing, and it's commonly confused in people's minds. There is a wonderful fellow, William Stanley Jevons, who was a Brit who worked at the height of the Industrial Revolution in the UK, and they were worried about coal running out in the UK. Right? Industrial Revolution is growing. He was particularly worried because he saw steam engines getting more and more efficient. He was an engineer, and his books have long discourses on how you build steam engines, and he was inventing economics. And he was worried that as steam engines got more efficient, you wouldn't use less coal, but you would use more coal because people would put them in more places. And he wrote this wonderful line that it's wholly a confusion of ideas to suppose that the economical use of fuels is equivalent to a diminished consumption. They are different things, efficiency and conservation. So a supply-limited situation. Right now, there's not enough electricity in China to meet the demand for air conditioning. If we make air conditioners more efficient, we'll keep more Chinese folks cool, but we will not reduce the demand for electricity because it's a supply-limited situation. A pretty good example is U.S. refrigerators. This chart, which has a Berkeley heritage, shows U.S. Refrigerator use versus time. The energy used per unit has gone down dramatically. The size goes up dramatically over 40-some-odd years or 50 years, and the price goes down also, largely because we're manufacturing them in China, I think. Okay. Nevertheless, you save energy by this kind of wonderful engineering. The problem is some of that can be offset because people have 2 refrigerators in their houses, right? So you don't capture it all. The U.S. automobile fleet is another good counterexample or instance. In the 1990s, the automobile mileage went up by 4.6% per vehicle sold. But if you open it up, what you see is that engine efficiency went up by 23% in a decade. Great engineering, right? Improvements in efficiency. But the weight of the vehicles and the performance of the vehicles gobbled up most of that efficiency. This was the decade in which the SUVs came in. Right? So you can misuse efficiency. In my opinion, if you want to induce conservation, you need to either raise the price of energy or you need to enact policies that force the reduction in its use. And either of those things is difficult for a government to do and remain in power. One last graph, last piece of data I think I'll show you. This shows state by state how much electricity each person uses per year in kilowatt hours against the average cost that's paid per kilowatt hour in cents. And the blue are the residential, and yellow commercial, and crosses are industrial. And what you see is that as electricity gets more expensive, people use less, right? Hawaii is the outlier out there, highest electricity price in the country, and almost the lowest use. California, much touted, indeed the lowest use per capita, but not so different from New York, which is slightly more expensive, and the whole group of New England states are over there. Contrast that with what goes on in Tennessee or some of these other unlabeled states where electricity is perhaps half the cost and the usage is correspondingly higher. I love the point in Washington, D.C. over there where they use a lot of energy. I mean, to be fair, that's the commercial point. There aren't too many people, but a lot of government activity in Washington, D.C. Okay. I can say something about lots of heat and no light, but I won't. Okay. Let me close with a couple of thoughts. Where are things going to go in the future? Hydrocarbons are going to dominate transport. We'll see a succession of conventional crude oil, heavy oils, biofuels, coal and gas to liquids that will give us continuity supply at reasonable cost. You can double vehicle efficiency if you want to. Hybrids, plug-in hybrids, other engine technologies can be deployed. You know, the gasoline engine is currently 25% efficient. At cost, it could probably be pushed up to 35 or even 40% efficient. It's a question of, do you want to pay for it or not? Hydrogen in vehicles, again, I'll leave to the question session if somebody wants to talk about that. In the power sector, we're going to see coal for reasons of energy security and gas for regions of cleanliness continue to dominate heat and power. The capture and storage of carbon, namely using the hydrogen for power, will be practiced if CO2 concerns are to be addressed. Nuclear, for reasons of both energy security and emissions, will be a fixed, if not growing, fraction of the mix. In fact, I would say if the world is serious about reducing CO2, 2.5 technologies are really important. The two technologies are nuclear, carbon capture and storage, or hydrogen power, and the half is wind. Renewables, like wind, will find some niche applications, but will remain a small fraction of the total. I think wind will get to 15% of electricity, perhaps. Advanced solar here is a wild card, I would say. If someone gets the right material, we could see solar really take off for electricity. And I'm cynical about demand reduction. It will happen only where it's cost effective or via policy. And CO2 emissions and concentrations are going to keep going up, absent dramatic global action, which we have not seen yet. What do we need to do around the technology? We need technically informed, coherent, and stable government policies. That may seem like an oxymoron, but I am an optimist. We need to educate decision makers about what can make a difference, what can't, and what's cost effective. And we need to educate the public so that they will support the decision makers in making those difficult decisions. As I go around the world talking about energy, much as I've talked to you today, I'm amazed at how confused and ill-informed people are about energy matters. As I said, we need to focus on the things that will give us the biggest bang for our dollar. For short and midterm technologies, I think we want to avoid picking winners and losers and have a level playing field for all applicable technologies. In power, you may know we have a renewable portfolio standard. What I would ask is, if carbon is the issue, carbon emissions, why don't we have a low carbon portfolio standard? Since, in fact, carbon capture and storage and nuclear are by far more scalable than any of the renewable technologies that we have available today. And they're low emission, of course. For longer term technologies, my favorites for pre-competitive research are methane hydrates, fusion, advanced fission, photovoltaics, biofuels, and so on. In business, we need a reasonable price of carbon. If BP is going to invest an extra $1 billion in producing an emissions-light power plant, it needs to have pretty good confidence that that reduction in emissions is going to be valuable 30 years in the future. Remember, 30 years is 15 Congresses and 7 presidential administrations, right? A lot can change over that time. Makes business a little bit reluctant to make big bets. And I think universities, as Berkeley has done and many other universities now around the world, are recognizing the importance of energy research, particularly educating people and doing research in the intersections of technology and policy together, since they really go hand in glove. Let me finish by noting that the energy climate nexus, which is what I've been talking about mostly, is, to my mind, only one example of a number of other big problems that are going to be coming down at us over the next couple decades. Those big problems include water, food, land use, non-energy materials. Those problems are driven by the economic rise of a third of humanity. They're driven by the finiteness of those resources in some cases. They're driven by the global nature of the world's economy these days and by technology themselves. They all have the characteristic that they intertwine technology with social considerations, and they all have the characteristic that they can be long time scale problems. Universities are wonderful settings in which to try to address those very complicated multidisciplinary problems. In fact, they may be the only institutions in society where we can do that. But at the same time, we need the involvement of business in that activity because, like it or not, business is how society gets things done. So that rationale is a lot of the rationale for the EBI that we have established here, which is working on one small piece of one of those problems, namely advanced biofuels. My guess is you're going to see lots of other activity of that sort involving problems beyond energy. And it's really important, I think, that universities step up to that challenge. With that, thank you for your attention. If you're interested, a video of this is available in streaming video on the web. You can hit fast forward if you've seen some of it already, but I think there is more material up there that will be of interest to you. Thank you very much.
So I'm going to get out of the way and let Steve field the questions himself, and you're off to the races.
Okay, good. Yeah, let's start in the back. Yeah.
Why is it widely assumed that moderate global warming, moderate, of course, is a subject of discussion, but moderate global warming would be a net gain for humanity over the next 50 years? I mean, is it so bad that if you could grow sugarcane in Siberia and Kansas, for a net gain?
Right. You know, I think what is destructive, if you like, or what's detrimental is the change itself. I think it's pretty clear that human society, nature, can adapt to almost any climatic conditions. I mean, humans live in a great variety of conditions already, from the Arctic through to the tropics, and we find plant and animal species all over. But if you start changing things rapidly, either up or down, you get tremendous disruptions. And I think that's what's really bad about the anthropogenic global change. It's the time scale of change. Yeah. Yeah.
You touched on peak oil theory earlier. I've read and seen quite a few interviews with oil executives.
Yeah.
I can't recall any of them except the theory of peak oil. Yet quite a few analysts who study the industry from the outside argue that peak oil theory is already here, if not soon upon us. I was wondering if you could explain why there's such a huge disparity.
Yes.
When they're probably aren't they looking at the same data?
Right. So just to repeat the question, lots of executives in the oil business will not buy into the peak oil discussion, whereas lots of analysts outside the industry do buy into it. And how do we explain that disconnect? Right? The world's international oil companies, the IOCs, Exxon, Shell, BP, and so on, right, have access to only about 15% of the world's reserves. They produce 35% of the oil produced every day, but they have only 15% of the world's reserves. For those companies whose CEOs you hear interviewed all the time, the horizon is getting more limited. It's all about access. And with the rise of resource nationalism, access becomes more and more difficult for those companies. You do not hear the CEO of Saudi Aramco interviewed talking about peak oil. nor any of the other CEOs of the NOCs, the national oil companies, who help produce and hold the reserves. So I think a lot of that disconnect is who's got access and who's producing. There is some debate also, as I mentioned, about the size of the reserves in some of these countries. But again, even if they're wrong by a factor of 2, I don't think there's going to be a problem. As the prices get more expensive, as oil gets more expensive, people go to more exotic forms of liquid hydrocarbons. We can turn coal into liquids at prices that are economic at, say, $60 or $70 a barrel. China's doing that already. It's making methanol out of coal and using it to run vehicles. The problem is it's a big capital bet, takes a long time, and it's CO2 awful, but it can be done. So it depends a little bit about what you call oil. If it's the stuff that flows out of the ground easily, that's finite. It'll peak at some point. But there's lots of other hydrocarbons, fluid hydrocarbons in the ground, as I mentioned already. Yeah?
Thank you. I hope that when we are calculating the cost of the different kind of energy, we are not, this is a comment and then a question, that we are not forgetting about how do you measure or how do you put in the cost of energy production, a high increase in rate of cancer around community that is by a nuclear plant, or how do we measure the devastation of biodiversity? Those has to put into account, and I don't think it's in any accountable books that. And the question is, 30 years ago, responsible scientists said, watch out with the irrational use of biofuels, otherwise we're going to have global warming. And here we are 30 years later having this. Now, responsible scientists are saying, watch out with the irresponsible use of biofuels, otherwise we're going to have a terrible ecological catastrophe. We don't know how to control the genetically modified organisms and the social implications for the third world, that millions of people are starving, and now those lands could be used for monocrops, and instead of for feeding that people, now feeding our cars, rather than changing our irresponsible way of life and reducing it. You see, California was wonderful. How do we expand that bubble? That's my question.
Yeah. So let me comment on the nuclear story and the cancer issue that you raised. France gets 80% of its electricity from nuclear power. Japan gets 30-some-odd% from nuclear power. To my knowledge, there's no epidemiological study that shows that cancer rates in France are higher due to radiation-induced cancers, nor in Japan. Okay? I'd be happy to be contradicted, but I believe that's true. If the evidence were there, I'm sure we would have heard about it. On the irresponsible use of biofuels, I'm with you 100%. I'm not happy about turning corn into ethanol. I'm not happy about turning sugar beets into ethanol. I'm not happy about palm oil the way it's done now. The reason that we established the EBI and put it here at Berkeley is because I want to do biofuels right. I want to optimize the yields. I want to not use food crops at all. I want to do it in a sustainable way. And some significant fraction of the funding or the projects that we're doing at the EBI are concerned with the socioeconomic aspects and with the ecological impacts. I don't want a crop field to be like an oil field. You know, you turn on an oil field and 10 years later, the production has fallen by a factor of 3 or 4. If that same thing happens when we start to plant energy crops, it's a bad idea. And so I want to do studies and research to try to see that we do it properly. And, you know, if we can't do it properly, we BP will not do it. Okay? Yeah. Yeah.
I agree with your conclusion that doing the policy is difficult. The U.S. Program for Energy Efficiency Standards started in 1979. California started about 5 years earlier. But it did have that success. As you showed on that slide, the average electricity consumption per new refrigerator has gone down 75% in that period of time. When we're talking about reducing carbon emissions by 80% in the next 40 or 50 years, that example is very relevant because we've just done it in the last 30 years for refrigerators. Yeah. The factual correction is that the refrigerators were responsible for about 26 million tons of carbon in the US in 1980, and are currently responsible for about 21 million tons of carbon. So the absolute amount of carbon emissions associated has gone down 20% in spite of larger and more refrigerators. Yeah. My question for you is, on the previous graph where you showed the cost per megawatt hour for electricity supply, have you considered looking at conservation, the cost of conservation, putting that on the same slide? I think you would find that it is cheaper and quicker than any of the supply options you show.
Yeah, you know, the whole negawatt discussion, I think that's great. You know, there are lots of economic and sort of human behavioral issues associated with conservation. I think it's not so much technology as policy and behavior. You perhaps have seen the McKinsey cost curves for carbon, which shows how much carbon you could save, how much carbon emissions you could save as a function of the carbon price. And there is a good chunk of emissions that's at negative price, which means you actually make money. Many of them have to do with energy efficiency, and that's a good thing. How come they don't get implemented? I don't know, you got to look in detail, but what I do know is not everything the world could do actually gets done. And the alleviation of poverty is probably the most outstanding example of that. We could do it, but we don't do it. Similarly, we could save a lot of energy, but we don't. How do we craft the policies or the economics in order to get those things to happen? Tough, I think. Nobody, you know, I mean, listening carefully to the presidential campaign right now, you want to cut petrol use, gasoline use in the US, a higher price will do that pretty effectively. Okay? No candidate wants to touch that at all. Right? In fact, you hear them saying exactly the opposite. Right? So until we get ourselves educated enough, I don't think that's going to happen. Yeah.
It strikes me that carbon sequestration is really the ticket, right? Because there's so much fossilized carbon that's still just loaded with energy, so we just suck it out, and we have hundreds of years to deal with this problem. So where does that stand now? Where is it going? What's the likelihood of things being implemented in the near future? What happened with this plant that suddenly the DOE decided not to build?
Yeah, future gen, right? Look, let me just make as a blanket statement, you know, carbon capture and storage is more than a notion. I mean, there are real projects on the drawing boards or things that have been implemented at small scale. But no one has yet built a commercial scale plant that integrates the gasification and the capture and the electricity production and the sequestration all together yet. So this is a gleam in people's eyes. BP is trying to make a business out of it, actually. We have announced 4 projects. The one most recently about a month ago in Abu Dhabi, gas-fired plant that would sequester the CO2 and help with oil production. Not one of them have we managed to carry through yet. The issues are not so much technical as regulatory. Whose CO2 is it when it's under the ground? Who has monitoring responsibility, liability, and so on? And economic. These things, particularly for the first few, are expensive, roughly twice as expensive as an ordinary power plant. Who is going to bear that extra cost? So it's going to take some government support or regulations or something like that. We have not yet managed to string those together for any of the projects we're attempting. And then there's the technical issue of when you put it under the ground, does it stay there? In depleted oil and gas reservoirs, which are the first reservoirs of choice, because we have pretty fair confidence that the carbon dioxide will stay down there because of the geology, well, that's fine. But most of the world's sequestration capacity is in aquifers, which have a much flatter geology, and it is plausible, but to be proven, that the CO2 will stay down there for 1,000 years. So to my mind, while it looks like a good idea and full speed ahead on demonstrations and research, I get a little uncomfortable as I hear non-experts talking about, you know, that this is the thing that's going to save us. Okay? There is no one thing, first of all, and secondly, we need to prove it. the world needs about 20 of these projects around the globe with different pieces of hardware, different geological sites, and so on, trying it out. And we haven't done one yet. So we got to get on with it. Let's go over on that side.
Every joule of energy that I use, I believe, ultimately becomes thermal energy.
Yeah.
And I think that's true for everyone in general and for companies.
Yeah, I think it's a law of nature, actually.
Right, the second law. Is that contribution to global warming completely swamped by the greenhouse gas emission capture of solar energy?
Yeah, so the world runs at something like 14 terawatts right now, and you can multiply by pi times 10 to the 7 seconds in a year and so on, and it's like 4 orders of magnitude less than the solar energy, whereas the CO2 radiative forcing is 2 orders of magnitude less, something like that. So it's small in the noise. Let's go in the back over there. Yeah, in the black shirt. Yeah.
What about the rumor I read today that the BP's renewable division is being cut out or spun off or discontinued?
Yeah.
I apologize for asking a difficult question.
Yeah, no, it's okay. One of the luxuries I have in the job I have is that I have no responsibility for any stuff like that at all, right? Okay. I do have a podium in which I try to educate people about what I think are the right things to do, but in the end, I make no decisions, which, after being provost for a decade is a wonderful thing. It's just absolutely wonderful. I think the actual statement, which was made at a strategy presentation by Tony Hayward, the CEO, is that we will try to maximize the shareholder value of our not inconsiderable investments in wind and solar. BP has a very large solar business. It is about to become, or is already, the largest or one of the largest wind operators in North America. We're putting in $1 billion, $1.5 billion a year into these businesses. They are worth a lot. The problem is, as they are buried in a big oil company that has revenues, not profits, but revenues of a couple $100 billion a year, it's not so easy to demonstrate to the shareholders the value of those things, to the markets in particular. So they're looking at ways of doing that. Beyond that, I don't know, okay? Whether it involves selling it off or an IPO or joint ventures and so on. I think all of those are ways of realizing that value. Okay. Let's go just back over there, and then we'll come down to the front. Yeah.
Yeah, I was wondering how the recent investment in Alberta tar sands corresponded with the goal of reducing the carbon footprint of your products.
Yep. Of the two drivers, security of supply and CO2 emissions, I think security of supply trumps CO2 any day for the near term. Not that I think so, but I think society behaves like that. We are doing tar sands. We'll probably do more of it, though again, I don't get into those decisions. What we will do is to try to do them in the most responsible way possible. And this is a small effort right now to understand how to do the refining better, eventually to understand how to do the extraction better. I think that's all one can say right now. Let's go down here, yeah.
There was an interesting plot in a recent Science that plotted the cost of solar power versus the installed power.
Yeah.
And the interesting thing about it, if you plot it on a log-log plot, it's a very linear plot over many orders of magnitude. And if you extrapolate up to 100 gigawatts of installed power, you end up with something like $1 per installed watt,
right?
Which would be quite competitive with many other sources of power.
Right. I don't know any data that isn't a straight line on a log-log plot, first of all. All right? Yeah, no, okay. Fine. That's one issue. I used to do experiments, so I know. Yeah, right. Okay, yes, we can do that. We can go through that. Yes, right. Look, it's a question of where you want to invest your money, because we don't have much time. We got about 15, 20 years to do that. And if you're going to invest that much money in solar, you have to ask yourself the question, if I invest a comparable amount to drive myself down the learning curve in CCS, in nuclear, we're not at the end of the line in nuclear technologies by any means, what's the most cost-effective thing to be doing? And I don't believe solar is it, although I'd be happy to be proven wrong.
Well, it's only multiplying by a factor of 10 what we presently have. I think we have something like 10 gigawatts now.
Yeah.
You have to go to 100 gigawatts.
No, let's be careful. When we say 10 gigawatts, that 10 gigawatts peak, right? Yeah, okay. Right, yeah. Well,
By the time you get to 100 gigawatts,
yeah.
you're down to about $1 per watt.
The world is producing solar about as fast as it can right now. We'll see what happens.
Have a Manhattan-style project.
Well, the analogy, so the question was Manhattan-style projects. I think the Manhattan-style analogy is really a specious one. Just consider that the Manhattan Project was to produce one gadget, or maybe two, right? Two different designs, gadgets. It had a single customer, right, who didn't care much about cost at the time. It worked in complete secrecy, didn't have congressional oversight, didn't have the media watching it, and only had to produce one or two things. That's exactly the opposite of energy, all of those factors, right? So I'm not a big fan of Manhattan-style analogies. Okay. Yeah.
Which seeks to develop nuclear energy?
Yeah. So are we interested in developing a division for nuclear energy? The answer is no. If you use nuclear energy for power, I think there are companies around the world who are much better at doing that than we ever could aspire to be. So the answer is no, although I think we understand that nuclear has to be a large piece of the picture going forward, if you look at the technologies. I would not exclude at some point in the future companies like BP looking at nuclear heat for the chemical processing that it does. That's a pretty effective source of low emissions heat. Now, the technology isn't there yet to do it. The high temperature reactors are just starting to come into commercial scale. But I can imagine in a decade or two, you might see companies starting to use that bit of nuclear as well. Yeah.
I'm of the generation, I guess, about as old as you are, that I switched from getting a PhD in physics or chemistry to getting involved in energy stuff at Lawrence Berkeley Lab. And so some of this has a sort of a deja vu all over again quality to it, because some of these things in general we saw 30 years ago. And what strikes me, and so the time frame there I think is relevant, because 30 years ago we saw some of these things and we talked about some of these things. Scaling was a little different, but nevertheless the nature of the problem was similar. And if we think we have 30 years in which to make a big change, seems to me the elephant in the room here is the political landscape. If you think about what happened, we can turn this into a question if you like, maybe it's just a comment, but if you think about the political landscape over the last 30 years, with a couple of exceptions, we've slid sideways, if not slid backwards in this country, with regards to fuel efficiency in car, I mean, just all sorts of things. I think Jim McMahon, probably the one sterling example that we can point to in some respects are things like we have gotten more efficient about some of the things, but some of that's been over the dead body of DOE, for heaven's sakes. And so the big problem here is and I mean, you've given a very compelling talk, and the problem is it's not you don't have to preach to the choir. The hard problem is it seems to me, is all of us preaching to the politicians that until 2 years ago were denying the existence of global warming.
Yeah. Yeah, again, from a sort of technical analytic point of view, the story is almost obvious. I mean, I hear Steve talk about energy, and I think we're in accord at the kind of 95% level on the analysis of what needs to be done and so on. Other people who've studied it also pretty much the same. So, the story and the actions needed are pretty clear. And what we need to do, as you say, is to keep talking to folks, keep getting the story out in the media accurately, and educating the politicians. We all vote, we all write to our representatives. That's the only way things are going to change. I agree that things haven't changed since the 70s, very much. Yeah, I know.
Well, I hate to break this up, but I actually agree with you. There is one real difference. The climate problem has, in those 30 years, has become really, and that's a huge difference. It's no longer been driven purely by local microeconomics. But I just want to say, I want to bring this to a close because Steve, we want to put a few hydrocarbons in him.
No, carbohydrates.
Carbohydrates. Sorry, excuse me.
There is a difference.
No. I'll go on record saying we'll put a little ethanol in them. Anyway, you've been a wonderful audience, and again, thank you, Steve.
Good.
Wonderful.
Thank you. Good.